Good morning, good afternoon, and good evening, everyone. So, today we're going to be continuing our statistical learning series. So, last time we talked about inference. So, just to briefly recap, what exactly is an inference? It's basically how we find some sort of relationship with our data, right? We're trying to generalize some relationship with our data. Unlike in predictions, where we're trying to predict, and our function here is basically what we call a black box. And what that means is we don't necessarily understand the behavior of our estimated function, this f with the arrow, the upper arrow. But comparing it to inference, here we do understand what is our f. We know how to associate its inputs with its outputs or its predictors with its response. And in doing so, as we understand this function, then we're able to determine some relationship. And now the question that we want to ask is, can we make some sort of equation or some relationship between these predictors or these factors as well as its responses or results, right? And so we went over how exactly do we estimate F. We introduced this idea of using training data. And our goal is to basically apply some technique or some math or some statistical learning to these training data in order to estimate this function f. And so we're going to talk about parametric methods now. And so yeah, this is where we stopped in the previous video. We're going to talk about parametric and non-parametric methods in order to estimate such a function that can help us predict or infer these stuff. Okay, so let's briefly talk about let's talk about parametric methods. So parametric methods actually involve a two-step model-based approach. So the first thing that we have to do is we have to make some assumption. Let me actually share what I'm reading. I'm going to the book. So we first have to make some assumption about the functional form or the shape, right? And so one very simple assumption is that f is linear, right? So that's the first step. So if you were to, so it's a two-step approach. So the first step is to make some sort of assumption of what the model is. And this is, humans will do this part, no math. So make some assumption about f. How do we want it to look like, right? So this is more on the intuition side of things. What's the shape of this thing? What's the shape of the data, right? This is how we kind of look at things. And so, for example, so I'll just give a, so here we just make some assumption about f, or in other words, the shape of the data. How exactly, or what exactly does this look like? You know how when you guys look at the clouds or the stars and you kind of like trace it with, I used to do that when I was young. I would like make up some figures of the stars and try to make some sort of shape based on my imagination. So that's something that we can do when making some assumptions. So this is a basic example, but is it a line? For example, f is linear about x. What do I mean? So, okay, actually, let me get a picture. So that's personally what I would do, making shapes of stars. You know when you guys just look at the stars and just make something out of it? So something like this. Let me, so here I'm gonna do some fun visuals. There we go. That's fun. So we try to look at the stars and we try to make some sort of shape with it. right? And if we go to our previous example, we did kind of do that. Hey, there, or this one, right? So here we kind of, am I sharing the right screen? Okay, good. So here we kind of made an assumption, or we kind of made a shape, or in this case, a line towards how towards this data, right? So this data has some sort of shape, and we're trying to describe it using a line, or we can see like a line there. So it's really similar to how we kind of just look at the stars during the night, and then we try to come up with shapes like these. So let's say f is linear, right? So if f was linear, then okay, now we're gonna go to the math notation. But it's basically our f. We input our predictors, right? And we say these are, okay, now I'm gonna get a little bit nasty here. This is what a linear function looks like. B2, B3, I don't even know, going all the way to BP. What do I mean by these? Depending on the number of factors that we have, that's gonna affect our line. And we call this a linear model. So this thing is called a linear model. And we will discuss this more in chapter 3, where we go into linear regression. Not right now. And so let's say now we have assumed that there's a shape in our data. So in this case, it's linear. Now the problem of estimating f is greatly simplified. So now we sort of simplify this function, whereas if we describe that whole shape, I mean, it could be something else, right? I mean, it doesn't have to be a line. It could be a circle, could be could be a square, could even be a star. I don't know. But once we have some assumptions, then our estimation becomes easier, right? So the idea is that instead of having, okay, actually, let me go back here. So instead of, here's what I'm reading. You guys might be wondering. Instead of having to estimate an entirely arbitrary p-dimensional function, one only needs to estimate the p plus 1 coefficients. Okay, this is a very mathy term. But what it's basically trying to say is that now we only have to estimate these numbers that we have. And these numbers are solely based on the number of predictors that we have. So if we had 3 predictors, then we have 4 coefficients because it's p plus 1. If we had 4 predictors, we would have 5 coefficients. If we had 6 predictors, we would have 7 coefficients. So it's always a plus 1. And this is, yeah, so this is a linear model fit by least squares to the income data from figure 2.3. And the observations are shown in red, and the yellow plane indicates the least squares fit to the data, right? So this is just a 3D version, right? Where we fit a line, or in this case, a line that's 2D. So let me actually just, I'll put this in my notes real quick. But this is a line in 2D. In this case, it's a plane. And we used a least squares method to do that. I did talk about it in a bit in my scientific computing series, but not too in depth. It's more of just getting the intuition of how to fit some curve or some shape or something to the data. Okay, so now that we've fitted these, well, here's the next step. So after we have selected some models, so in this case, a linear model, now we need to have some sort of procedure. And we use the training data to fit or to train the model. And so in the case of the linear model, Now we need to estimate the parameters B naught to BP. That is, we want to find values of these parameters such that, there we go. So we want to find these values. These are numbers, right? These are numbers such that they're estimated to be the output Y. And so this is more or less how we can predict or how we can infer something. And then the most common approach to fitting the model is referred to as ordinary least squares. So this is a method on how we can fit a curve to a model. And we're going to discuss this in chapter 3. However, least squares is one of the many possible ways to fit the linear model. In chapter 6, we discuss other approaches for estimating the parameters. Okay, let me just share my notes real quick because I want to write that out. So step 1 was making an assumption about the shape of the data. So in this case, we made an assumption of a linear model solely because maybe I think it's basic. Now, after we select a model, now we need some sort of procedure. So find a procedure and do the procedure, obviously, that uses our training data. So we're going to use that training data to fit. Or in other words, to train the model. So fitting and training surprisingly are the same things because I'm taught from a programming perspective that we train some machine learning model to some data that's really just coded basically. But here underneath the hood, actually, it's more about fitting some curve to the data, right? And so in this case, okay, so that's the idea. And then the mathematical sense is we want to find some output such that this whole thing, our linear model here, B2, I'm assuming this is all the way to BP, right? Okay, let me do a summation here. This goes from some K0 all the way to P. Then we say this is, oh, actually, we can put an X naught, so we can do a summation. Or actually, we could do a summation here. This would be B naught plus. Okay, now I'm trying to make use of a mathematical sense because I feel like this is going to be easier for us in the future. It starts at 1, it goes all the way to P. So this is B, K, X, K. There we go. So we add all of this all the way to P. And then we use this B naught. And the idea being is that we want to sort of fit this. So we want to find these coefficients, these numbers, and then we plug them in, and then we find this Y, or something that's close to Y, or our response. Okay, let me go back. So it's more or less just an introduction of how this is going to go. The model-based approach just described is referred to as parametric. And the idea is that it reduces the problem of estimating F down to one of estimating a set of parameters. Assuming a parametric form of F, for F rather, simplifies the problem of estimating F because it is generally much easier to estimate a set of parameters such as B naught to BP in the linear model, right? So it is easier than it is to fit an entirely arbitrary function F, right? So just to reiterate, we want to, again, assume the data has some shape. We find, or this is where we come into play. We decide some model, so in this case, a linear model, and we're going to try to estimate the parameters. So B naught to BP, B naught to B sub P. In that linear model, in order to try to estimate our output. And usually this is easier in our chosen model compared to if we fit it to some arbitrary function f, right? However, the potential disadvantage of a parametric approach is that the model we choose will not always match. So it doesn't always match the true unknown form of f. Sometimes it's too far from the true f, so our estimate will be poor. And so we can try to address this problem by choosing more flexible models, right? And these models can fit many different possible functional forms for f. But in a general sense, fitting a more flexible model, well, there's a, a consequence, and that's we want to estimate more parameters. And these more complex models can lead to a phenomenon known as overfitting the data. When we say overfitting, meaning they follow the errors or noise too closely. And so if we follow it too closely, then once we input new data, well, that's the issue. We don't take into account that adjustment, right? As much as possible, we don't want to overfit the data because if there are new data, then how can we make sure that we're predicting it correctly, or how can we make sure that our model is good enough for those new data, right? So I'm going to give an example of overfitting, actually. So an example of overfitting is that, let's say we have okay, I'm going to keep it simple. We have this, say this is our graph, right? Let's say, since I'm used to math, I'm going to do yx, but let's say this was, let's do one of our examples. This was what was it? I think it was the years of education. So that's this axis. Then we had here the income. Then we have some data points, right? These are the data points. Assume this is 30. I don't know. And we fit some model here, right? Now here we can kind of see so first we identify the shape, right? So the shape is kind of like a line when you think about it. Okay, I didn't draw the line, but and then now we draw the line. So there's our linear model, right? And then from there, well, okay, now we have some errors, right? There's an error, there's an error, there's an error, and many more, right? Those are errors. Now, okay, from here, what's the next step? What's overfitting? Oh, well, yeah, now we fit the model and then we do some technique to fit the parameters. Well, we haven't done that yet. We're probably going to do it in code maybe. Because this is quite long when we do it by hand. But okay, so what's overfitting? When we overfit, well, we're essentially doing this. So that's overfitting. It's like we're trying to get every data point in our curve. So what if we had new data points like these? I don't know. Well, then how can this doesn't really help us indicate that. Unlike, let's say if we had, oops, what did I do? But that's overfitting. We're fitting the model too much that it becomes less useful for new data points, right? So let's say we had, I don't even know how this works, something like that. Then maybe a model that we could have is like a sine function, something like this. I'm not super sure, but this is, yeah, it's kind of like a sine function now that I think about it. Yeah, it looks like a sine function. Yeah. So the idea is that we shouldn't overfit. right? There's a trade-off that's happening. We actually might get into it. It's basically called the bias variance trade-off. So if we overfit the data too much, well, there's less variance, more bias, right? Because we're more biased on the data. But then if we underfit or well, then that's more variance. So it opens up to more variety, but then it's less bias. We'll talk about it. It's the bias variance trade-off at some point, maybe not here. It would be funny if we talked about it in the next slide. But okay. So that's the idea of overfitting. So one thing to note, I guess, from that is overfitting. If we do an overfitting, well, actually we don't. Oops. Okay, I will not talk about it here. Yeah, we're not gonna talk about it. They didn't talk about the issues yet. I was trying to get into it, but never mind. In a later video, maybe. Okay, so okay, let me just go back to my shared screen. So figure 2.4 shows us an example of the parametric approach, and we apply this to the income data from figure 2.3, and we fit a linear model of the form. So our income, which is our response, and then our parameters b naught plus b sub 1 times the education. So that's one of my predictors, the education. Another one was the seniority. And then we sort of fit it here. And we call this, so this is a spline fit. So now least squares fit, but a spline fit. And we talk about that in a bit later in chapter 7. But there's a way to fit this linear model to the income data, pretty much, right? Okay, let me just, so there's a way to fit it. Yeah, so there's a more, so you notice, right, when we try to fit the parameters, so we're gonna do it in code, I think. We compare it to something like this. So this is the same problem. This is a linear model using least squares technique. We'll talk about that. It's basically a line. If you think about, oh wait, I'm showing the wrong screen, am I? Okay. So this is basically a line. Uh, there we go. It's basically a line. But then if we actually try to fit it, we find the coefficients in code or somewhere, then we're gonna get something like this. And so this gives us lesser error on the data points. So this is a quote unquote better model, right? And again, if we do the math, well, this is income as my response or output. And then this is my fitted linear model, education. Then I add it to my seniority, right? Cool. Okay, let me go back. So now we have assumed a linear relationship between the response as well as its two predictors. The entire fitting problem reduces to estimating B0 and B1 and B2. And we're going to do this. We're going to estimate these three numbers. These are basically numbers. We're going to do it using least squares linear regression. Now, what in the world is that? Well, we're going to see that later in a bit. Comparing figure 2.3 to 2.4, so that previous one, the linear fit is, let me see. We can see that the linear fit given in figure 2.4, so that previous one, is not quite right. So this one's not quite right, according to the book. Don't ask me. True F has some curvature that is not captured in the linear fit. So it wasn't captured there. However, the linear fit still appears to do a reasonable job of capturing the positive relationship between the years of education and the income, as well as the slightly less positive relationship between the seniority and the income. So it still works, right? It's still a reasonable model, right? It's still a logical model to implement. It may be that with such a small number of observations, this is the best we could do, right? So now we're trying to get into the conceptual idea of how exactly do we predict and infer using the statistics behind things, right? Okay, now we're going to talk about non-parametric methods. Now, non-parametric methods do not make explicit assumptions about the function, right? So here we actually don't make assumptions. Okay, this is a new topic even for me. Instead, they seek an estimate of f that gets as close to the data points as possible without being too rough or wiggly. Now, what exactly does that mean? We'll get to it in a bit. Such approaches can have a major advantage over parametric approaches, right? So by avoiding to assume a shape of the data, then there's a potential to accurately fit a wider range of possible shapes. So that's that idea, right? If we had varying data, well, this is a better method to use, right? For analyzing data. Okay, so any parametric approach brings with it the possibility that the functional form used to estimate f is very different from the true f, right? So there is always, if we do a parametric method, well, there's always that possibility that the estimated f is different from the true f. And in this case, it would result to the model not fitting the data well. However, when we're using non-parametric approaches, it actually, so surprisingly, it completely avoids this danger because we don't assume anything about the shape of the data, right? No assumptions made. However, here's the caveat. Non-parametric approaches do suffer from a major disadvantage, and this is they do not reduce the problem of estimating f to a small number of parameters. All right, so we don't estimate f based on some small number of parameters, but a very large number of observations, far more than is typically needed for a parametric approach, is required in order to obtain an accurate estimate for f. So let's kind of summarize what we talked about there. So we kind of just touched upon when exactly is it effective to use either one of these methods. So we're saying this is better to use if we have more data, right? So larger data, then that's effective, right? What else, where else can this be? Okay, larger data, since no assumptions on the shape of the data, right? We didn't make or we don't make any assumptions on the data, and so this is more effective when we're given a large number of data, right? Yeah, pretty much that's it, right? Okay, let's go back. So an example of a non-parametric approach to fitting the income data. So let's go back to the income with the education and the seniority is shown in figure 2.5. So this thing. So that's actually a non-parametric way. So the spline fit is a non-parametric method of fitting the data, right? So there's a thin plate spline that's used to estimate F, and this approach does not impose any pre-specified model on F. Instead, it attempts to produce an estimate for F that is as close as possible to the observed data, subject to the fit, that is. And so that yellow surface in that previous figure being smooth, well, yeah, that's it. And in this case, the non-parametric fit has produced a remarkably accurate estimate of the true F shown in figure 2.3. Right? So it's a better, so in this case, it's a better estimate compared to a parametric approach to this data, right? Now, okay, this is, I think, a procedure on how to do this, but in order to fit a thin plate spline, the data analyst must select a level of smoothness, right? And here we have a similar figure. This is a rough, thin plate spline fit, but it uses a lower level of smoothness, allowing for a rougher fit. Now, the resulting estimate fits the observed data perfectly. However, the spline fit shown in figure 2.6 is far more variable than the true function F. And so there's the case of overfitting, right? So when we load this in 3D, well, we're trying to kind of overfit. So we're trying to get all of those data points into the curve. And sure, in some cases that's good, but it is, again, an undesirable situation. Again, it's that overfitting idea. It's undesirable because the fit obtained will not yield accurate estimates of the response. Let's say if we have new predictions or new observations that were not part of the original training data set. So that's the big caveat behind that idea, right? So I kind of explained this before, but if we try to fit the data too much, well, then if we give it new data, well, that's not really gonna work, right? And so we discuss methods for choosing the correct amount of smoothness in chapter 5, and then splines are discussed in chapter 7. So it's more on that in the later chapters. So as we have seen, there are advantages and disadvantages to parametric and non for statistical learning, and we explore both types of methods throughout this book. Okay. So yeah, we're trying to just do more conceptual. There's more of a conceptual understanding behind the later things to come. We even talked about, okay, yeah, these are more stuff. Okay, I'm not even gonna, yeah, so that's it for that part. So yeah, I'm actually gonna stop the video here. So the idea is that I'm just trying to go over each idea, right? Step by step. I'm not trying to overload this thing. So basically, just to briefly recap what we talked about how we can estimate some function after the data, whether that's fitting a curve. And we can do that using two methods. Those are parametric and non-parametric. For parametric, we have to assume that the data has some shape, and then we fit some model accordingly. And then at the very end, we have to adjust the parameters, right? And I'm not sure how they do it here, but in my calculus classes, we compute it. Here, maybe we code it. I'm not super sure. Haven't done any implementation yet. But at least we get the conceptual understanding. And then for non-parametric methods, this is more on not making assumptions of our data, right? So we're open to as many changes in the data as we see in the future, right? And this is the idea that the curve adjusts as we put in more data. So as we put in more data, our model gets quote unquote better, but we're not trying to make it too better, or we're not trying to make it the best model, because if we try to, then that's basically overfitting. And if we overfit and we try to put in more data, well, then that's a quote unquote disaster, because that's not going to be an effective model. Think of it like I'm taking a test. Let's say we're taking a test, right? And so we're training ourselves, or we're studying, right? We're training ourselves to take that test. And we say that, oh, okay, well, if you give me the same test as the thing that I've practiced with, then I basically memorized everything from that previous practice test or that training data. And then I apply that to the test data, right? Then I'm going to get a perfect score, right? But if we leave some of the data to be the training data, we leave some of it to be the testing data, then we'll actually get to see how effective our model is if it encounters new data, right? So that's a more programmatic approach of things. So we're gonna give the program more, or we're gonna give the program some training data and some testing data. So we split that too. We train the model on the training data, and then we test it, see if it works. And then we use it on the testing data, see if it works. Right? So it's that idea of, yeah, here it's the parametric and non-parametric, but that's for a programmatic approach. Right? Okay. So I'm gonna stop there because I feel like I've yapped too much. So yeah, next video we're gonna talk about what's this trade-off. So I think we kind of touched upon it a bit, but we're gonna see. We're gonna see. So what's the trade-off between accurately predicting something as well as interpreting the model? Right? So we're gonna see how does one affect the other, right? But that's for a future video. Anyways, I hope you guys enjoyed. I hope this was interesting. Personally, I think this was pretty interesting. And I'll see you guys in the next video.